We have already discussed input characteristics. So common emitter configuration. And in common emitter configuration, we have already discussed input characteristics. Input characteristics, or it is also known as forward bias characteristics. Bias characteristics. And we discussed that input characteristics of common emitter configuration, it also looks like the VI characteristics of diode. VI characteristics of diode. So somewhere near 0.7, the diode junction will turn on and the current will increase abruptly. And this plot, forward characteristics, is basically between input voltage and input current. So it is VBE, which is in volts, and input current is IB, which is in microamperes. IB is in microamperes. So in common emitter configuration, the transistor looks like something this. Um, we have emitter common to both terminals, input and output. So some voltage is applied between base and emitter, which is known as VBE, that is the input voltage, and current that flows into the circuit, it is IB. Okay, then you have output characteristics, which will be drawn between VCE versus IC. IC is the output current. IC is the output current. Now see, uh, IC is the output current. Uh, Now see, if we change the VCE, it will have impact on input current, IB also. It will have impact on IB also. So our transistor is basically like this. We have somewhere we have emitter, then we have base, and then we have collector. Okay, so this is N, it is P, and this is N, and this is emitter, this is base, and this is collector region. And whatever voltage is applied between base and collector, it is known as VCB. It is known as VCB. Okay, it is known as VCB. It is known as VCB. So VCB will be something like this in general. So VCB. So it is VCB. Now see, VCB is generally reverse biased. VCB is generally reverse biased. So in collector, we have N-type collector and we have base, which is P-type. So in P-type, we will have holes. Majority of the carriers will be holes. Then we have acceptor atom. Okay, we have acceptor atom and a hole. We have acceptor atom and a hole. But near depletion region, near depletion region, there will be no hole present. Only acceptor atoms will be there. So this is an acceptor atom. This is an acceptor atom. In P-type semiconductor, this is an acceptor atom here also. Okay. Similarly, in N-type semiconductor, we will have donor atoms. We will have donor atoms donating an electron. Donor atoms donating an electron. And in depletion region, there will be only donor atoms. So there will be only donor atoms. There will be only donor atoms. And I have already told you in the last class, in previous class, that this width, this is known as width of base. This is WB. This is the actual width of the base. Actual width of the base. And suppose the width of the depletion region is W. Suppose the width. Roll number 38. Can you hear me better?
Yes, sir. Now.
ठीक है, am I audible clearly?
Yes, sir. Yes, sir. Clearly.
Okay, fine. So I'll resume now. My connection got somehow disconnected. Anyway, so I said that then we can calculate the effective width. Effective width can be then calculated. Effective width of the base. Effective width of the base will be equal to actual width, which is width of base, minus the depletion region. Minus the depletion region. Okay. So this will be the effective width of the base. Effective width of the base. And we also know that VCE, VCE, that is voltage between collector and emitter, it is equal to VCB plus VBE. Okay, how it is equal to like that? See, VXY is basically equal to VX minus VY. VXY is a general term which is equal to Vx minus Vy. Similarly, we can say that VCE is equal to Vc minus Ve on one hand side, on the left hand side. So if we observe right hand side, VCB plus VBE, it will be equal to Vc minus Vb plus Vb minus Ve. Okay, then Vb and Vb will be cancelled and we are left with Vc minus Ve, which is nothing but which is equal to VCE. VCE. That is why I said that VCE, it is equal to, in a transistor, VCE is equal to VCB plus VBE. VCB plus VCE. Okay. VCB plus VCE. And that is quite logical also. If I draw a transistor here, for example, this is collector, this is base, and this is emitter. VCE is this much, and VBE is this much, and VCB is this much. VCB is this much between collector and base junction. Okay, and we can then say VCE is equal to VBE plus VCB. VBE plus VCB. 38 ठीक है बेटा ये?
Yes, sir. Yes,
रोल
sir.
नंबर 38. What about 27? 27 आपको समझ में आया?
जी सर.
Okay. Now see, from this equation, so we have two equations here. One is equation 1 and we have another equation, equation 2, for example. From equation 2, if we see that, we observe that if we increase VCE, now see, in equation 2, VBE is constant. VBE cannot be changed because VBE is always constant in transistor. VBE is always constant in transistor. And VBE, the value of VBE, show me what is the value of VBE? Shomia is not here.
Yes, sir. Yes, sir.
What is the value of VBE better? What is the value of VBE?
The value of VB is always, the Rishasa always 0. Constant.
नहीं खुदा इन सहल क्या हुआ आपको? What about Ifra? Ifra is here. Ifra, beta, what is VBE? Ifra,
Sir, yes, sir.
what is the value of VBE?
0.7 volts.
Huh, very good. It is 0.7. In transistors, I said in the class also, we take it 0.7. And 0.7 is a constant value. So VBE cannot be changed. So in equation 2, if VCE increases, what will happen to VCB? VCB will also increase. VCB will also increase. Okay, if VCE increases, from equation 2, if VCE increases, VCB is bound to increase. VCB is bound to increase because equation 2 is VCE is equal to VCB plus some constant, which is equal to 0.7. Okay, and if VCB increases, if VCB increases, if VCB increases, if VCB increases, what will happen to W? W is the depletion region. If VCB increases, what will happen to the depletion region? Depletion region. Roll number 6 is here. Roll number 6. If VCB increases in the diagram, what will happen to the depletion region W? Afnan? Afnan?
Yes, sir.
What will happen to W if VCB increases?
Sir, sir, the W region, WB region,
Huh? W.
sir, it will increase.
It will also increase. If VCB increases from the diagram, जो diagram मैंने बनाई है यहाँ पे, okay, you can see that this is W here, the blue one. Blue one is W. So if VCB increases, depletion region, because it is it is reverse bias junction. Collector base junction is always reverse bias. If VCB increases, W will also increase. Reverse bias means more width of the depletion region. More width of the depletion region. So if VCB increases, then width of depletion region, which is basically W, will also increase. It will also increase. Okay, it will also increase. Now see, if width of depletion region W increases, if W increases, what will happen then to effective width? What will happen to effective width? If W increases, roll number 76, what will happen to effective width of the base?
So effective width would
76.
also increase.
It will increase from the diagram. From the diagram, please note it down here. If W will increase, what will happen to effective width?
Sir, but sir, emitter base junction is thin here, so
What will happen to effective width? See,
it will
effective width, it is equal to WB minus W. So you have a mathematical relationship, something X is equal to Y minus something. So if this term increases, what will happen to
decrease.
it? Will decrease. And it is also evident from the diagram. Effective width plus W, they are equal to actual width. जब W increase होगी तो effective width को कम होना ही है, ठीक है? If this term will increase, it is a negative term. So this has to decrease then. This has to decrease then. This has to decrease. So effective width of the base decreases then. Effective width of the base, it decreases. Okay? Effective width of the base decreases. Why I am saying so? Because effective width, it is equal to actual width minus depletion region width. If depletion region increases, then effective width has to decrease. It has to decrease. It has to decrease. Okay. Now see this phenomenon when width of the depletion region increases and effective width decreases. This is known as base width modulation. Basically, we are trying to modulate the width of the base junction. Base junction's actual width is constant, but effective width changes with the change in the depletion region and with the change in VCB. So this process is known as base width modulation. Base width modulation. And how does base width modulation happen? Because of change in VCB. Because of change in VCB. As VCB changes, base width modulation is attained. You can modulate the width of the base. You can modulate the width of the base. Now see, if now effective width of the base decreases, now effective width has decreased now. If effective width of the base it decreases. Uh, बुशरा बेटा आपको ये समझ में आया जो अभी तक मैंने ये डिस्कस किया?
जी सर।
What about मुर्तजा?
जी सर।
मोमिन?
Yes, sir.
आपको समझ में आया बेटा मोमिन?
जी सर।
ओके, अबरार?
जी सर।
Okay, should I repeat it? मैं इस discussion को very quickly should I repeat it?
No, sir.
Okay, not required. Now see, focus on this discussion now. If effective width of the base decreases, it also means that the area where there is a chance of recombination, जो recombination जहाँ पे होती है, because base is already thin, and there is a very small area where the charges emitted by the emitter will recombine. Once the effective width is small, अब देखिए effective width तो ये है जहाँ पे थोड़ी सी recombination मिल जाती, जहाँ कुछ ना कुछ holes where some holes were available for the electrons which were emitted by the emitter. Some electrons which were emitted by the emitter, they want to recombine now in the base. So some region should be there. So that region will be not definitely depletion region, because in depletion region there are no free charge carriers. So the region outside the depletion region is basically effective width region. तो जहाँ पे कुछ ना कुछ charge carriers हैं. So when this effective width region it decreases, it means that the chance of recombination also decreases. It means now chance of recombination also decreases. So if effective width decreases, then we say that then recombination region of base narrows down. It is very important. So recombination region of the base also narrows down. This is a very important phenomenon. Now it means that when the recombination region of the base narrows down, it means the base current will not be now that much stronger. It will be further weaker. That will also decrease. Okay, because the recombination region is small now, so base current is also it is only recombination current. Now it means then base current will decrease. So if recombination decreases, recombination region decrease would mean recombination overall decrease. If recombination decreases, then base current IB also decreases. IB also decreases. Okay, IB also decreases. Now see what will be the effect on input characteristics. This is our input characteristics. I'll draw it again now. Now our input characteristics will be now modified. It will not be actually what we have seen there. They will look like that, but with the help of VCB, they will change. Okay, so you have IB on this axis, it is in microamperes, and you have VBE here, which is in volts. Actually, the VI characteristics, they look like this, and this was somewhere 0.7 volts. 0.7 volts. Okay. Now, as VCB increases, as VCB increases, as VCB increases, it means then IB decreases. IB decreases. Okay. We have already seen it. As VCB increases, IB decreases. So there will be this curve now. You will have another curve now, like this, something like this. So this will be for VCB, for example, equal to 1 volts. VCB equal to 1 volts. Okay. Or we can say VCE, whatever is the case. VCE and VCB, they are related, directly proportional. And this one, it will be for higher VCB. VCB equal to, say, for example, 10 volts. Okay. And this one, third one, it will be for still higher VCB. VCB equal to 20 volts. So as you increase, as you go on increasing the VCB, then the current IB will go on decreasing. Current IB will go on decreasing. That we have already traced out. As VCB increases, IB goes on decreasing. It goes down. Okay, its magnitude decreases. Is it fine? किसी को कोई क्वेश्चन तो नहीं है? रूल नंबर 27 आपको बेटा ये समझ में आया ये बात?
जी सर।
ठीक है, इसमें कोई परेशानी तो नहीं है?
नो सर।
ओके, व्हाट अबाउट 14?
यस
रोल
सर।
नंबर 14 बेटा समझ में आया?
जी सर।
सुहैब 64?
यस सर।
समझ में आया बेटा?
यस सर।
हाउ अबाउट अरबा?
ये से समझ आ गया ये।
ओके, ठीक है। ऑलराइट, ठीक है। Okay, we'll go now for output characteristics of common emitter. So this was all about input characteristics. So we'll discuss now output characteristics. Output characteristics. Output characteristics of common emitter configuration. Common emitter configuration. And as you know that output characteristics, they will be basically, it will be a plot between output voltage versus output current. Output current. Okay, it will be plot between output voltage and output current. And if we try to understand what is the output voltage here, it is VCE. Output voltage here is VCE. And what is output current? Output current is IC. Okay, output current is IC. So it will be a plot between IC versus VCE. IC versus VCE. Okay. And so output current in common emitter configuration is IC. Input current in common emitter configuration, it is IB. It is IB. We have already seen it. We have already observed that. Okay, IB and IC. So input current is IB and output current is IC in common emitter configuration. What will be then current gain? Current gain, it is equal to output current divided by input current. What is output current here? It is equal to IC. What is the magnitude of IC? It is in milliamperes. Okay. What is input current? Input current in common emitter configuration, it is IB. and magnitude of IB is in microamperes. It is in microamperes. And current gain here in common emitter configuration, B is represented as beta. If you remember, we discussed last time in our class that in common collector, in common base configuration, current gain is represented by alpha. And the value of alpha is somewhere near 0.96 to 0.998. But beta is current gain. Current gain in common emitter configuration. So current gain here in common emitter configuration, it is not represented by alpha, it is represented by beta, common emitter configuration. So beta will be equal to IC by IB, okay, which is basically some current in milliamperes and some current in microamperes. Now see, milliamperes is a large current and microamperes is a smaller current. It is a smaller current, okay? So the value of beta, it is somewhere, practically it is somewhere near 90 to 300. 90 to 300. The value of beta is somewhere practically 90 to 300. Its value practically. So what is beta? Beta is nothing but the current gain. Beta is nothing but current gain. Okay. The way we used to represent in common collector current, we said IC is equal to IC majority plus IC minority. हमने ये ऑलरेडी डिस्कस किया है क्लास में. इसी तरीके से यहाँ पे भी हम उसको डिस्कस करेंगे and we will be able to find out that I may derive this equation somewhere, but you can also try it at your home. IC is equal to beta times IB. वहाँ हमने देखा था alpha times IB. Okay. Then beta plus 1 times ICBO. ICBO. Okay. ICBO. And remember that ICBO is the reverse leakage current in common base configuration. Although we are using here in a common emitter configuration, but we can represent it in this configuration. We can represent the current IC in terms of reverse leakage from common base. We'll be shortly transforming it to common emitter. Okay. Now see here in this equation, if IB is equal to 0, if IB is very small and it is equal to 0, then we know then from this equation IC will be equal to 0 plus beta plus 1 ICBO. ICBO. Okay. So IC will be equal to beta plus 1 ICBO, which is nothing but it is small current. It is small current, but in common emitter configuration. And what kind of small current it is? It is reverse leakage current in common emitter configuration. Therefore, it can be represented by ICEO. ICEO. Okay. ICEO. Now we can say that IC equal to beta plus 1 ICBO. It is equal to ICEO. That is the reverse leakage current in common emitter configuration. In common emitter configuration. समीरा बेटा ये ठीक है, कोई क्वेश्चन तो नहीं है? समीरा, what about अरबा?
Yes, sir.
ठीक है, ये आपको समझ में आया?
Yes, ये समझ आ गया.
तौहीदा को समझ में आया?
जी सर.
Ayman 78.
Yes sir.
मुर्तजा,
जी सर.
सईद शमसुल आफाक,
यस सर, आया समझ.
उबैर.
जी सर.
Okay, all right. So this is the reverse leakage current, and if you remember from our class, reverse leakage derivation of reverse leakage current was the first step in our output characteristics. Okay, in our output characteristics. Now see, if we draw the output characteristics now, we said In the beginning, it is IC versus VCE. Now we will draw a graph. We'll draw a graph like this. So it is IC versus VCE. This is IC, which is in milliamperes, and we have VCE, which is in volts. VCE in volts. IC versus VCE. Okay, so we have IC and VCE. Now see, when IB is zero, IB is zero, what is our collector current? Collector current is equal to reverse saturation current in common emitter configuration. So this is true basically, I'll draw it here. This is true if IB is equal to 0. Okay. Now I can now say if IB is 0, what is my collector current? It is equal to ICE equal to, this is equal to ICE 0, ICE naught. That is the reverse leakage current. So I can draw it somewhere here from the graph. Like this. So this current is for IB equal to 0 microamperes. 0 microamperes. This is equal to 0 microamperes. 0 microamperes. Okay. And how much is this? This is quite higher. It is quite higher than ICBO. जो हमारी common base configuration थी, उसमें इसकी width थी ICBO. But here it is quite higher than ICBO. How much higher? It is beta plus 1 times ICBO, which is basically ICEO. So it is quite higher than the reverse leakage current of common base configuration. That is why it is, a little bit higher than x-axis. In common base configuration, it used to be nearly closer to the x-axis. वहाँ ये हुआ करती थी, बिल्कुल x-axis के close होती थी. But here it is a little bit higher. It has a larger magnitude. Keeping in mind that beta has a larger value, 90 to 300. So suppose if beta is 300, it is 300 plus 1 means 300 times or 301 times. Okay, 301 times ICBO, and ICBO, if it is small, it will be definitely larger than that. So that is why I have marked this first line greater than ICBO as compared to common base configuration. Okay, so the next line will be now like this. So this is for some IB. यहाँ अब IB 0 नहीं है. It is some non-zero quantity. Say for example it is 4 microampere. For example, it is 4 microampere. Then the second curve would be like this. Third curve is like this, and then it goes like this. Okay, so definitely they are uniformly spaced. So this will be some value IB equal to, for example, 10 microamperes. This may be IB equal to 20 microamperes, and this is equal to IB equal to, say for example, 30 microamperes, and then this may be IB equal to 50 microamperes. So at different base currents, you will have different levels of collector current. Different levels of collector current. Okay. Different levels of collector current. And I have already told you that am I audible?
Yes, sir.
Roll number 29. Roll number 29.
जी सर जी सर
ठीक है बेटा?
yes, sir.
Okay. All right. ठीक है. And here on y-axis, the current could be somewhere here. Say for example, this is first one is 0.5 milliampere. फिर हो सकता है यहाँ 1 milliampere होगा. Then you have 2 milliamperes, and you have 3 milliamperes, and so on and so forth. You have 4 and 5, 4 and 5 milliamperes. Okay, and sometimes we can calculate beta from this graph also. कभी कभार हम इससे beta भी निकालते हैं. How do we calculate the beta? Beta is basically current gain. Beta is in common emitter configuration, it is current gain, or we can also say that it is known as amplification factor. Amplification factor is beta in case of common emitter configuration. And we can see from this graph, beta can be calculated by change in IC, delta IC by delta IB. What is beta? Beta is basically IC by IB, and it can be calculated by delta IC by delta IB. Delta IC by delta IB. Suppose you want to observe this graph, this line. Okay, we want to observe this line. Then we can observe the changes. For example, if we want to observe in this way, अगर हम इसको ऐसे observe करेंगे, यहाँ से लेके all the way up to here, how much IC has changed. So it changed from 3 minus 1, for example. 3 पे पहला coordinate है, and यहाँ पे 1 पे दूसरा coordinate है. So it will be 3 minus 1 milliampere. अब यहाँ से हम divided by IB भी देखेंगे. IB कितनी change हुई? 20 microampere से 10 microampere. So it will be something like this. 3 minus 1, ये सारा milliampere है. Then it will be 20 microampere minus 10 microampere. अगर ऐसे हो रहा है change, and you will be able to find some value of beta. In that case, you will be able to find the value of beta. For example, okay, let us read it in some other lecture. Okay, so this was output characteristics. Now see, here if you observe these curves, they are not constant. Remember, I said that in common base configuration, the curves are constant. They do not have any slope. They are parallel to x-axis. Why? Because input current was equal to output current there. वहाँ पे जो input current थी, that was input current was IE, and output current was IC. So this was in common base configuration. लेकिन यहाँ पे जो input current है, जो यहाँ है, वो है IB, और जो यहाँ पे output current है, वो है IC. This is in common emitter configuration. And this one is smaller. अब देखिए ऊपर जो common base में थी, वो दोनों equal है. IC is nearly equal to IE. Yeah, IE is nearly equal to IC. But here in common emitter configuration, that is not the case. तो common base में क्या था? Common base में input current was nearly equal to output. यहाँ input current, here you do not have input current equal to output current. That is why the curves will not be constant. They will have some slope. Okay. So we should note it down here. Curves are not constant. Now see here also, we know that VCE, we know here VCE, it is equal to VCB plus VBE. We have already discussed it in our previous point. हमने पहले भी देखा था जब वो base width modulation हमने इस lecture में discuss की थी. So VCB we already know, VCE is equal to VCB plus VBE. Now see, if VCE increases, what will happen to VCB? VCB will also increase. And if VCB increases, if VCB increases, what will happen to effective width? We have already seen it. Effective width decreases. If effective width decreases, what will happen to base current? IB, we have already seen that IB will also decrease. If IB will decrease, okay, if IB will decrease here, IC increases. IC increases. Why does IC increases? IC increases because more electrons will be collected by collector. More electrons, because you do not have now base width. बेस में कोई width है ही नहीं जहां recombination होगी, तो जितने भी electrons emitter से emit होंगे, so this is your, for example, this is your emitter, this is your base, and this is your collector. Now you are saying that base effective width of the base, it is very small, so all the electrons, they will be collected by the collector. There will be very small space where the electrons will be recombined in the base. So base current will decrease. Eventually, all the electrons, no electron will be wasted in base, or it will be allowed to wander in the base. They'll be collected directly by the collector. Therefore, here we can expect that more electrons will be collected by collector. More electrons will be collected by collector. So I said that when the base region will decrease, then more electrons will be collected by the collector. If more electrons will be collected by the collector, what will happen then to IC? IC will increase. IC will increase. Why? Why will IC increase? Because more electrons or charge carriers emitted by emitter will now be collected by the collector. So it will be collected by the collector. Okay. So therefore, what can we conclude? If VCE increases, I said that if VCE increases, IC will increase. Okay. If VCE will increase, IC will. If VCE increases, IC will increase. So this plot is basically between IC versus VCE. So we are expecting that if the curve is like this and VCE goes on increasing, so the curve will not be flat like this. In other words, because IC increases with the increase in VCE, then it will be like this. Slightly इसकी भी increase होगी. That is why it will have slope. Okay, that is why it will have slope. Otherwise, as was the case in common base configuration, there was no slope in the output characteristics. लेकिन यहाँ output characteristics different होंगे, क्योंकि जो ही हम VCE increase कर रहे हैं, then base width modulation happens. And because of that base width modulation, lesser recombination will happen in the base. When the lesser recombination happens in the base, it means whatever electrons they are emitted from the emitter, जितने भी electrons emit हो रहे हैं, वो base में कभी recombine नहीं होंगे. तो हो सकता है 100 normal sense में, in normal case we would emit, for example, 100 electrons and 10 will recombine in the base and they will correspond to base current. But once base width modulation happens and the effective region of the base narrows down, then in this case now you are emitting 100 electrons, only 2 electrons are recombining. So 98 are now collected by the collector. So in this case now, the collector current is more than the previous one. Previous में तो collector current 90 electrons से थी. अब जब आपने base rate modulation हो गई because of VCE, तो अब आपकी collector current ज़्यादा हो गई. So what I am trying to say that base width modulation is not a deliberate attempt. You are not actually doing it. It happens naturally because of the regions, because of the depletion regions. ठीक है? Base already कम होती है, जो ही आप, और काफी ज्यादा सेंसिटिव भी होती है. बेस इज वेरी नैरो and it is sensitive in the sense that whenever you apply a reverse bias across its junctions, it will create a large depletion region. When you increase the reverse bias, the depletion region will increase much more prominently. ठीक है? And because of that, effective width, or a region which is having some electrons or some charges which will facilitate recombination process, it narrows down. When it narrows down, IB effectively decreases. And if IB effectively decreases, collector current is bound to increase. It is bound to increase. That is why you have some slope here. Roll number 54, beta, आपको ये समझ में आया what I am trying to say here? 54.
यस सर रिपीट कीजिए।
अच्छा ठीक है, चलो ठीक है, ध्यान से समझो इसको, मैं दोबारा एक बार रिपीट करता हूँ. प्लीज पे योर अटेंशन. अपने फोन की तरफ ध्यान दो. So what I was trying to say that in common emitter configuration, जो हमारी output characteristics हैं, it looks like red color line, यानी वो parallel होती है x axis की, voltage axis जो है. लेकिन इन कॉमन इमिटर कॉन्फ़िगरेशन, वो तो कॉमन बेस कॉन्फ़िगरेशन में होता है, लेकिन कॉमन इमिटर में ऐसा नहीं होता है. कॉमन इमिटर में कुछ स्लोप होता है, यानी ये थोड़ी इंक्लाइंड होती है. तो देयर इज अ डिफरेंस बिटवीन आउटपुट कैरेक्टरिस्टिक्स इन कॉमन बेस एंड कॉमन इमिटर. अब सवाल है कॉमन इमिटर में ऐसा होता क्यों है. ठीक है, कॉमन इमिटर में ऐसा क्यों होता है? तो वो इसलिए होता है बिकॉज इट हैपन्स बिकॉज व्हेन यू इंक्रीज VCE, व्हेन यू इंक्रीज VCE, जब हम VCE को इंक्रीज करते हैं, VCB increases because if you see from this equation, VCE is directly proportional to VCB. तो जब VCE इंक्रीज होगा तो VCB भी इंक्रीज होगा. VCE is directly proportional to VCB from this equation. So जब VC इंक्रीज होगा, VCB इंक्रीज होगा. जब VCB इंक्रीज होगा, इफेक्टिव विड्थ कम होगी बेस की, क्योंकि हमने ऊपर बेस विड्थ मॉड्यूलेशन ऑलरेडी पढ़ी है. जब इफेक्टिव विड्थ कम होगी तो IB भी हमने देखा, बेस करंट कम होगी. तो जब बेस करंट कम होगी, IC इंक्रीज होगा. बेस करंट जब कम होगी, कलेक्टर करंट इंक्रीज होगी. वो क्यों? क्योंकि बेस करंट एक्चुअली कम इसलिए होती है बिकॉज यहाँ पे जो नैरो इफेक्टिव रीजन होता है, जहाँ बेस करंट जनरेट होती है बिकॉज ऑफ रिकॉम्बिनेशन, अब वो कम होता है. बिकॉज द रीजन, इफेक्टिव रीजन जहाँ रिकॉम्बिनेशन होती है, वो बेसिकली डिमिनिश होता है, उसका एरिया कम होता है. और जितने भी इलेक्ट्रॉन्स इमिटर से अब जाएंगे, वो तो पहले बेस में जाने थे. दे वेर सपोज टू गो टू बेस, क्योंकि वहां उनके लिए एक स्टेशन था, एक छोटा सा स्टेशन. अब वहां जगह है ही नहीं, तो वहां रीजन और नैरो हो गया है, तो ये डायरेक्टली फ्लाई कर रहे हैं to collector. So they are directly collected by the collector. So they do not find a recombination partner in base. So it means more electrons will be collected by the collector. It means more electrons will be collected by the collector. So जब more electrons will be collected by collector, it means then IC current increases. IC increases. Collector current increases. So that is what I am trying to show here. जो ही VCE increase होगा, so we can now conclude that from this discussion, जो यहाँ इतना जो ये लिखा है मैंने, इससे हम कर सकते हैं conclude that I will write it down that if VCE increases, what will happen? IC also increases. Okay, so this is the summary of the discussion. अगर VCE increase होगा, ICE also increases. So I will try to show this now in the graph. Now see, if VCE increases, अब ये increase हो रहा है यहाँ से, what will happen to IC? IC constant नहीं रहेगा, अब ये भी increase होगा. तो अब ये linearly increase होगा. अगर ये बराबर increase होता linearly, अगर ये linearly बराबर होता, तब ये ऐसे होता कर्व. अब इसको इतनी ज्यादा लीनियर रिलेशनशिप नहीं है, डायरेक्टली प्रोपोर्शनल तो है लेकिन पूरा भी नहीं है. सो इट इंक्रीजेस विद सम स्लोप. द स्लोप इज वेरी स्मॉल, दैट इज व्हाई इट हैज सम स्लोप. तो अगर आप देखेंगे यहाँ, आई हैव मार्क्ड द कर्व्स विद सम स्लोप. मैंने इनको कुछ स्लोप डाला है यहाँ पे आउटपुट कैरेक्टरिस्टिक्स में. तो क्यों डाला है ऐसा स्लोप? मैंने इनको ऐसे क्यों नहीं बनाया बिल्कुल पैरेलल टू एक्स एक्सिस? क्योंकि कॉमन एमिटर कॉन्फ़िगरेशन में ऐसा नहीं होता है, उसमें कुछ स्लोप होता है. Please watch my video after I finish the lecture. You should watch it carefully and take these points. उसके बाद बॉयल स्टेट को एक बार दोबारा देखें आराम से, and then you will be able to understand this thing. ठीक है, तो आपको फिर थोड़ा सा समझ में आ जाएगा, वरना आपको समझ नहीं आएगा. और ये बहुत ही अहम कॉन्सेप्ट है, इसमें आगे बहुत सारी चीज़ें इस पे डिपेंडेंट है. Now see, this is the VI characteristics of output characteristics of common emitter BJT in common emitter configuration. Okay, so these are the VI characteristics of BJT in common emitter configuration. Okay, here also you have some regions. We have some regions here. So one region is somewhere here. This is one region, and it is known as region A. There is another region which is somewhere here. A region somewhere here, which is known as region C. And there is also a region somewhere here, which is the green region. And this region is known as region B. This is known as region B. Okay. So in VI characteristics, especially output characteristics, there are three regions. So what are these three regions? Region A, then you have region B, then you have region C. Okay, region A, B, and C. Now see, A region, it is known as saturation region. Region B, it is known as active region. And region C, it is known as cut-off region. It is known as cut-off region. Okay, and please remember that region B is more important region. It's very important region. Active region. Region B is very important region because it is mostly used in a BJT for amplification. Okay, this region is used for amplification of input signal. This is used for amplification of input signal. Okay, so region B is more important region. We'll be mostly discussing this region. Okay, but we'll also discuss region A. Region A is the cutoff region. So as far as region A is concerned, so region A, which is cutoff region.
Saturation region.
Sorry, it is saturation region, not cutoff. Okay. So region A, yes, it is left. So it is saturation region. It means you are attentive also. Some students are listening. Saturation region. Okay. So region A is saturation region. And we know that in saturation region, what is the case in saturation region? Both the junctions are forward biased or they are reverse biased?
Forward bias.
Saturation, forward biased? Okay. So both the junctions are forward biased. Okay. So if they are forward biased, normally VC is reverse biased. Emitter based junction, collector based junction is reverse biased. तो जब उसको forward bias करेंगे तो उसकी polarity जो होगी VCE की, तो we can say in region A, VCE that used to be positive in forward bias, in reverse bias, in active region, वो होता है यहाँ पे negative. So it is VCE is minus times VCE. Okay, it is minus times VCE. And we also know, but VCE it is equal to VCB plus VBE. That is the equation number 2 जो हम अभी तक डिस्कस करते आ रहे थे for base width modulation. Okay, so we can say that minus times VCE using equation minus times, अब यहाँ VCE है तो इसको minus times VCE रखेंगे, minus times VCE. Why I'm taking minus times VCE? Remember I said that in common emitter configuration, अगर this is for example NPN, this is N, P and N transistor. So this is the polarity of VCE. This is the polarity of VCE. अब ये है, अगर इसकी polarity ऐसे है, then it means it is reverse biasing the collector base junction. It is reverse biasing. लेकिन अब अगर इसको करेंगे forward bias के लिए आपको इस forward bias के लिए आपको इस voltage source को ऐसे बनाना है, ठीक है? तो as compared to the previous configuration now, VCE is equal to minus times VCE. Then only it can forward bias, because in saturation region both the junctions are forward bias. तब जाके ये forward bias करेगा. So that is why I said VCE is equal to minus times VCE. So I am substituting instead of VCE minus VCE, which is equal to then VCB plus VBE. Okay, and we can say then you have VCB here. All right. Okay. So VCE can be equal to, अब यहाँ minus था, अगर if we multiply, I'll write it down. Multiplying both sides by minus 1. If we multiply both sides by minus 1, we have, what will be we having? VCE will be equal to minus times VCB, then minus times VBE. Or we can say that VCE is negative. VCE is negative. So in saturation region, VCE is always negative. And that is quite we can observe it from here also. In this region, saturation region, VCE is negative. Please observe it here, negative. This line does not mean that you have 0 here. It doesn't mean. You can have 0 somewhere here also. You can have 0 here also. Or the curves could be more, अगर ये ऐसे भी हो, ये कभी-कभार ऐसे हो सकती हैं, थोड़ी towards y-axis, closer to y-axis. I have drawn it closer, away from y-axis. तो ये कभी-कभार closer to y-axis हो सकती हैं. But we should remember that in saturation region, VCE is always negative. So in GATE, you have certain questions sometimes. For a saturation region operation in BJT, VC is positive, VC is negative, VB is positive, VB is negative. तो ऐसी कोई combination वहाँ दे देते हैं वो, in order to check your knowledge. But if you know from the graph, अगर आप graphs को analyze करोगे, अगर आपके जहन में VI characteristics होगी, output characteristics होगी, common emitter configuration की, तो आप immediately कहोगे कि VCE is definitely negative. Okay. Now, it means that if VCE is negative, it means that VCB is now forward biasing potential, and वो होता भी है, इसमें दोनों potential, दोनों junctions forward bias हैं. VCB is now forward biasing potential. Okay, forward biasing potential. So in saturation region, I already told you that both the diode junctions, this is your base and this is IB and this is your IC, and somewhere it can be IE. Both the junctions, diode junctions D1 and D2, they are both forward biased. Okay. They are both forward biased. Hence, we can say then, hence D1 is forward biased. And if D1 is forward biased, then then the direction, अभी तो reverse bias में उसकी direction ऐसी थी collector current की. Normally, if it is reverse bias, say for example, then the direction of IC is in this way. But if it will be forward biased, then the direction of current will be in this way. Okay, so if the biasing condition of the D1 changes, then direction of IC will change. It will also change. When you change the biasing condition, direction is bound to change. Okay, so this happens in saturation region only. This happens in saturation region, and this happens in saturation region. This happens in saturation region. You should also remember that sometimes it is also given in saturation region. In saturation region, even if these curves are away from y-axis, अगर IC axis से ये curves थोड़ी away होगी towards right hand side, then we also say it is also said in saturation region, VCE is very small. Okay, this is VCE. We say VCE is very small. It is nearly equal to 0. In saturation region, sometimes we also say VCE is very small. It is 0. जो ये VI characteristics हैं, whether these curves will be away from y-axis or closer to y-axis, they actually vary from BJT to BJT. किसी बीजेटी में डोपिंग कंसंट्रेशन ज्यादा होती है, जैसे या कोई पावर बीजेटीज होते हैं, उनकी थोड़ी थोड़ी डिफरेंट हो जाती है. सो दैट्स व्हाई आई एम चेंजिंग माय नैरेटिव्स एट टाइम्स कि VCE तो जनरली नेगेटिव होता है, बट इफ इट इज नॉट नेगेटिव, इट कैन नॉट बी पॉजिटिव, इट विल बी वेरी स्मॉल. देन ये पॉजिटिव कभी नहीं हो सकता है. इट कैन बी इक्वल टू 0. VCE इज नियरली इक्वल टू 0. तो हो सकता है इसमें पॉजिटिव वैल्यू हो कभी 0.1 वोल्ट, 0.2 वोल्ट, 0.3, but not more than that. So these curves, the shape of the curves, it also varies from BJT to BJT, but more or less they are like that. वो ऐसे ही होती हैं. इनमें एक slope होता है and they are quite distinguished at different base currents. जैसे मैंने ऊपर base currents बनाई हैं. ठीक है, तो अगर इसमें भी हम देखेंगे इस वाली curve में, इसमें भी अगर हम देखेंगे, the region which is towards the left of this yellow line, it is the saturation region. And what is VCE here? VCE, if we assume this is 0 axis, VCE is nearly equal to 0 here, and mostly it is negative क्योंकि ये towards left of this line is the region. Okay, so this was about region, it was about region A. Is it fine? ठीक है बेटा. रिजवान, आपको समझ में आया ये?
जी सर.
कोई सवाल तो नहीं है? What about
No, sir.
बुरहान is here? बुरहान नहीं है. तो उर्फी है यहाँ पे?
जी सर.
आपको समझ में आया बेटा ये?
यस सर.
ओके. साहब को समझ में आया?
Yes, sir.
Are you sure?
Yes, sir.
Okay. ठीक है. So this was about region A. Okay, it was about region A, which is saturation region. We will talk about region C now. इनमें हमें थोड़ा सा डिस्कशन करना है रीजन ए और रीजन सी के बारे में, बिकॉज मोस्ट ऑफ आवर डिस्कशन विल बी बेस्ड ऑन रीजन बी. वी मे स्पेंड डेज ऑन रीजन बी मोस्टली. ठीक है, इसमें हमें बहुत टाइम देना है. तो थोड़ा थोड़ा हल्का फुल्का एक इंट्रोडक्शन होगा अबाउट ए एंड अबाउट सी, रीजन सी. सो रीजन सी इज एक्टिव रीजन. Rehab, region C is active region?
No, sir.
It is?
Cut-off
Which region? It is cut-off
Cut-off.
region. Okay. So region C is cut-off region. Region C. So region C, it is cut-off region. It is cut-off region. Okay. Region C is cut-off region. And if you remember from my VI characteristics, it is somewhere here. The first curve. So this region is all the way here. This is the cutoff region. Our cutoff region is somewhere here. And the first curve here, IB is 0. IB is 0 microampere. And we also said that what is the magnitude of the current above x-axis? It is equal to ICEO. ICEO, that is the reverse saturation current in this region. So in this region, some current will flow equal to reverse saturation region. Now see here, in cutoff region, IB can be equal to 0. IB can be 0 or it can be less than 0. Less than 0 microamperes. IB can be 0. IB can be 0 or it can be less than 0. अगर ये positive होगी, then the curves will go like this. Okay, तब ये ऊपर जाएंगी curves. तो definitely ये positive तो नहीं होगी, या तो 0 होगी या तो less than 0. So IB is less than 0. IB is less than 0. So if IB is less than 0, it means IB is negative. If IB is negative, then direction of IB will change. ठीक है, तो ये एक सिंपल सा कॉन्सेप्ट है. इफ यू हैव सम वोल्टेज सोर्स, तो अगर इसमें करंट IB है पॉजिटिव यहाँ से फॉर एग्जांपल, तो अगर IB को नेगेटिव बनाएंगे देन इट विल चेंज इन दिस डायरेक्शन, तो अब इसकी डायरेक्शन उल्टी हो जाएगी ऐसे. सो दिस इज IB माइनस टाइम्स IB. जो ऊपर है वो है प्लस टाइम्स IB. ठीक है, वो प्लस IB है. तो when the sign of the current changes, the direction also changes. So if IB is less than 0, it means IB is negative. If IB is negative, then the current direction should also change. So if IB direction is reversed, it means then D2, where is D2? D2 is this one. It means then D2 is reverse biased. Okay, in cutoff, the base emitter junction is reverse biased. Okay, so it means D2 is reverse biased. D2 is reverse biased. So we have one diode between collector and base. We have another diode between base and emitter. So you have emitter, collector, you have base. So this is D2 and it is reverse biased here. This is D1. So D2 is reverse biased. If D2 is reverse biased, then the direction will change. IB direction will change. Okay, then the direction will change. So if D2 is reverse biased, IB direction changes. IB direction changes. It changes. Now see, since we know it that VCB, it is equal to VCE minus VBE. Okay, and we also know that VCE is much greater than 0. VCE is much greater than 0. Since VCE is not 0, generally it is much greater than 0. VCE is much greater than 0. I also told you what is the magnitude of VCE normally. Normally it is of order of 9 volts because it is collector to base potential. तो ये जनरली होता है 12 वोल्ट्स भी होता है, कभी कभार ये 9 भी होता है, कभी 10 भी होता है. तो it is not 0. It is much greater than 0. In fact, it is much greater than VBE also. VBE जो होता है, VBE is generally 0.7. लेकिन VCE generally होता है 12 volts, 9 volts, 10 volts. So it is much greater than VBE also. It is sometimes 20 times greater than this. So sometimes it is 15 times greater than this. Okay, so VCE is much greater than 0. If this is much greater than 0, then what will happen? Because of that, what will happen? D1 can be easily reverse biased. Okay, तो क्योंकि इसमें easy reverse bias होता है. In cutoff region, you should remember that D1 and D2 both are reverse biased. Why is D1 reverse biased? Because VC is much greater than 0. VC is much greater than 0. तो N side पे collector में क्या है? N side, NPN. We are talking about NPN. So collector is N type, then you are applying certain positive voltage. It means it is easily reverse biased. It is easily reverse biased. So we can say that both D1 and D2, they are reverse biased in region C. In region C, they are both reverse biased, and this happens only in cutoff region. This happens in cutoff region. Cutoff region. तो cutoff region में ऐसा होता है. ठीक है, तो we are left with region B now. Region B को हम करेंगे postpone because we'll be spending most of the time there. इसमें काफी ज़्यादा time हम spend करेंगे. So we have now third configuration, which is known as common collector configuration. Common collector configuration. And in common collector configuration, you know that collector is common to both input and output ports. So if this is N, P and N device, and you have somewhere here emitter, you have base here, collector is the common terminal. Collector is the common terminal. And your input voltage will be between collector and base. Collector and base. So the current that will flow into the base, it is known as IB base current. And voltage between B and C, it is known as VBB. Okay? It is the base voltage, what is applied at the base. And we know that input junction should be forward biased. That is why you have connected positive terminal to P and negative terminal to N. Okay? And you also know that output junction should be reverse biased. Output junction should be reverse biased. So in that case, output voltage is connected, it is connected between collector and emitter. Collector and emitter. It is known as VEE. And this is the polarity. Since it should be reverse biased, that is why you have connected a large positive to collector also, N side. Okay, so this is IE direction. This is IC here, so you have IB here, VEE. तो इसमें कभी कभी ये कंफ्यूजन होता है कि आपको VEE का जो नेगेटिव है ये तो N साइड के साथ है. Why is it not forward biased, the output junction? But you have to basically remember that collector based junction is forward biased. ठीक है, इसमें I'll explain this effect here, shortly after a few explanations. इसमें एक configuration होती है जिसको हम कहते हैं emitter follower. So we also take output from emitter terminal in common collector configuration. तो उस जगह पे ये थोड़ा clear हो जाएगा. Anyway, but I will try to first make the symbol of the BJT here in common collector configuration. So in common collector configuration, you have emitter at the top, then you have base terminal and collector at the bottom, and this is your base terminal. So this is base, whatever comes inside is IB, and whatever leaves here is IE, because this is emitter terminal, और यहाँ है collector terminal, और जो इसके अंदर जा रहा है वो है collector current. Now see, the voltage between B and C, it is definitely VBC. It is VBC. Okay, it is VBC. And the voltage between collector and emitter, it is known as VCE. And between base and emitter, it is known as VBE. Okay, so these are the three markings. You have emitter here, you have collector here, and you have base here. So this is the common collector configuration symbol of BJT. ठीक है, ये इसकी symbol है. And we can see that from this diagram, we can see that VCE, it is equal to VBE plus VBC. VBE plus VBC. Okay, so VCE, it is equal to VBE plus VBC. That can be seen from this diagram. So output characteristics, if we see here in common collector configuration, first of all, अगर हम इसकी output characteristics देखेंगे, output characteristics, they are basically between output current versus output voltage. Okay, so output current is IE. And what is output voltage? It is VCE. Output voltage is VCE, and this will be for various levels of input current, that is for various levels of IB. तो हमने यहाँ पे भी output characteristics देखी थी in common emitter configuration. These are basically various, this is a curve plot between IC versus VCE, but for a particular input current. This is input current. So for various input currents, there will be various curves. As you change input current, इनकी curves भी change होती जाएंगी, जैसे यहाँ पे दिखाई गई हैं. So similarly, I'm saying that it will be a plot between IE and VCE for various levels of input current, that is IB. Okay. And we also know that हमने already देखा है in common base configuration, IE is equal to, or IC is equal to alpha times IE. In common base configuration, we have already seen that IC is equal to alpha times IE, and we said that alpha is the current gain in common base configuration. Alpha is current gain, and its value is 0.95 to 0.998. We have already discussed it. So if we consider that its value is 0.998, it means it is closer to 1. And in that case, we can say IC is nearly equal to IE. IC is nearly equal to IE. मेहराज जी समझ में आ रहा है? 68. मेहराज दीन. What about Aruja? Aruja को समझ में आ रहा है?
Yes, sir.
तो मेहराज दीन को रिमूव करते हैं. अच्छा. What about Junaid Bhatt? 46 को समझ में आ रहा है?
Yes, sir.
रिहाब को कोई कंफ्यूजन तो नहीं हुआ? रिहाब?
जी सर, नो सर, कंफ्यूजन नहीं हुआ।
हाँ ठीक है, ये जो मैं इस वक्त डिस्कस कर रहा हूँ ये हमने कॉमन बेस में ऑलरेडी किया है. दैट इज व्हाई मैं अपने ही साथ आई एम डूइंग अ सेल्फ रीडिंग काइंड ऑफ थिंग. इट इज समटाइम्स ये काफी ज्यादा ऐसी फनी है, बट लेट मी डू इट. सो IC is nearly equal to IE. We have already discussed it in our common base configuration, and even in common emitter, IE is also nearly equal to IC. In general, BJTs में IE हमेशा IC के बराबर ही होती है. थोड़ी सी इनमें फर्क है, उतनी ज्यादा नहीं है, बिकॉज तीसरा कंपोनेंट इसमें IB है, तो उसका मैग्नीट्यूड ऑलरेडी कम होता है. तो if IC is nearly equal to IE, then there is an important conclusion. What is the conclusion? Output characteristics of common collector configuration are nearly equal to output characteristics of common emitter configuration. क्योंकि इसमें देखिए आउटपुट कैरेक्टरिस्टिक्स ऑफ कॉमन कलेक्टर किसके दरमियान है? इट इज बिटवीन IE एंड VCE. लेकिन अगर हम कॉमन इमिटर की देखेंगे, कॉमन इमिटर की है बिटवीन VCE एंड IC. अब यहाँ सिर्फ फर्क है IE में, बट वी नो दैट IE इज नियरली इक्वल टू IC. IE is nearly equal to IC. तो जो आउटपुट कैरेक्टरिस्टिक्स है कॉमन इमिटर कॉन्फ़िगरेशन की, बिल्कुल हूबहू लगभग वैसी ही है आउटपुट कैरेक्टरिस्टिक्स in common collector also. So if I draw common collector configuration output characteristics, तो इसमें भी ऐसी ही होंगी, कुछ ऐसे, something like this for different input currents. So this can be IB equal to 0 microampere. इसी तरीके से यहाँ होगा IB equal to say for example 1 microampere, IB equal to 10 microampere, IB equal to 20 microampere, and then IB equal to say for example 30 microampere. लेकिन दिखने में तो है ऐसे ही है. And IE here it will be in milliamperes. VCE here it will be in volts. VCE will be in volts. Okay. VCE will be in volts. VCE here will be in volts. And please remember here in common collector configuration, in common collector configuration, please note it down that current gain is represented by gamma. यहाँ जो है current gain उसको gamma से denote किया जाता है. So current gain, or we can say amplification factor here is represented by gamma. It is represented by gamma. And what is gamma equal to? Gamma here output current is IE. Output current is IE. What is input current in common collector configuration? This is IB. ठीक है, ये common collector configuration है. तो gamma is always equal to IE by IB. अब देखिए IE, value of IE is nearly equal to IC. तो in that case it will be IC by IB. What is IC by IB? It is beta. तो गामा का वैल्यू भी नियरली बीटा का वैल्यू ही होता है. In fact, गामा is equal to beta plus 1. तो गामा और बीटा का वैल्यू जनरली सिमिलर होता है, थोड़ी सी फर्क होती है. हम इनको will derive certain relationships that will help us to understand how they are related. हम वो चीजें करेंगे, ठीक है. So we know that, so you should remember that gamma, the value of gamma, which is basically current gain in common collector configuration, beta is current gain in common emitter configuration, alpha is current gain in common base configuration. Gamma and beta का value same ही होता है, similar होता है, if not same, exactly same, but alpha is quite less, it is nearly equal to 1. ठीक है. So we can say that, but we know that IE it is equal to IB plus IC. This is the golden equation of the BJTs. ठीक है, ये एक basic और बुनियादी equation है. IE emitter current is always equal to collector current plus base current. Therefore, and we also know IC it is equal to alpha times IE plus ICBO. ये हमने already common base configuration में ये चीज डिस्कस की है. Equation number 2. आप please refer to the notes. Okay. IC is equal to alpha times IE plus ICBO. Okay. If we substitute the value of equation 2 in equation 1, substituting equation second in equation 1, we will have then IE will be equal to alpha times IE plus ICBO plus then we have IB. Okay, then we have IB. Okay, now you have IE here, then you have IE here. Okay, so यहाँ है equal to. So we have IE on left hand side, then we have one term on right hand side. If we rearrange them on left hand side, we will be left with 1 minus alpha into IE. It is equal to IB plus ICBO. Okay, or we can say that IE is equal to IB divided by 1 minus alpha plus ICBO divided by 1 minus alpha. लेफ्ट हैंड साइड से हमें 1 माइनस अल्फा था, इसको डिवाइड किया हमने, ठीक है, ऑन राइट हैंड साइड, और we can see dividing equation 3 by 1 minus alpha, we obtain the next equation. Now 1 minus alpha here, 1 minus alpha, it is known as current amplification factor in common collector configuration, 1 divided by 1 minus alpha, and it is equal to gamma, so it is equal to gamma. So what is gamma? It is current amplification factor. So first relationship we were able to find, gamma is equal to 1 divided by 1 minus alpha. तो alpha के साथ इसकी ये relationship है, ठीक है. So hence we can say that IE here it will be equal to gamma times, अब इसी equation को equation 4 we can say, hence from equation 4 we can say that IE it is equal to gamma times IB plus gamma times ICBO, So this equation is valid for common collector configuration. ये equation common collector के लिए use होगी. Now we will derive what is the relationship between alpha, beta and gamma. Remember that alpha, beta and gamma, alpha is nothing but it is current amplification factor in common base, okay. And we generally say that alpha can be alpha DC. Alpha DC means current amplification of DC current. And alpha can also be alpha AC. Alpha AC means current amplification of AC component of the current. Okay. If it is DC component of the current, alpha DC is always equal to IC by IB in case of IC by IE in case of common base configuration. Alpha AC hoga change in collector current. Change because AC component is always changing. Okay. So if this is IC, so how much IC changes when this current moves from this point to this point? तो शायद इतनी change हो रही है. So this is delta IC. Okay. So delta IC divided by delta IE. When VCB is constant. What is VCB? VCB is the biasing voltage at the output. यानी DC को चेंज नहीं कर रहे हैं, सिर्फ AC वोल्टेज चेंज हो रही है, तब आप अल्फा AC निकाल सकते हो. इसी तरीके से हर किसी करंट कंपोनेंट में, करंट गेन में, एम्प्लीफिकेशन फैक्टर में DC कंपोनेंट भी होता है, AC component भी होता है. So we can say that we have beta DC also, which is nothing but, what is beta DC equal to, Rizwan? Rizwan is here. खुशबू है?
Yes, sir.
खुशबू जी, what is beta AC now? Beta DC equal to, what is first of all beta equal to? Beta is current gain in common emitter configuration. तो common emitter configuration में आउटपुट करंट IC होती है, इनपुट करंट क्या होती है वहां? रिजवान? हाँ, IB. Yes, it is IC by IB. इसी तरीके से इसका AC कंपोनेंट होगा डेल्टा IC डिवाइडेड बाय डेल्टा IB. ठीक है, तो ये बहुत ही आसान है, प्रोवाइडेड DC वोल्टेजेस आर कांस्टेंट. DC बायसिंग इज कांस्टेंट, DC चेंज नहीं हो रही है, तभी हम AC निकाल सकते हैं. इसी तरीके से जो गामा है, अब गामा इज द एम्प्लीफिकेशन फैक्टर इन कॉमन कलेक्टर कॉन्फ़िगरेशन. तो प्लीज रिमेंबर, ये जो अल्फा बीटा गामा, इसमें अक्सर बच्चों को कंफ्यूजन होता है, व्हाट आर दीज, पढ़ के भी उनको पता नहीं होता है व्हाट इज अल्फा बीटा एंड गामा. These are all current gains in 3 different configurations. अब इनका वैल्यू अलग अलग होता है, इसीलिए हमने इनको 3 नाम दिए हैं, वरना हम एक ही दे सकते हैं। तो गामा डीसी भी होगा जिसका मैग्नीट्यूड होगा बराबर IE बाय IB। इसी तरीके से गामा AC भी होगा जिसका होगा डेल्टा IE बाय डेल्टा IB when VCE is constant. VCE is constant. Okay. So what is the relationship? The relationship can be derived now. तो ये पहले 3 टर्म्स हैं, अल्फा बीटा एंड गामा है क्या, अब इनकी रिलेशनशिप होगी। Now see, since we know IE it is equal to IB plus IC, ये BJT की बेसिक इक्वेशन है। इमिटर करंट इज इक्वल टू कलेक्टर करंट प्लस बेस करंट। Dividing both sides by IB. When we divide both sides by IB, we will have then IE divided by IB is equal to IB divided by IB plus IC divided by IB. What is IE by IB? Nighat, what is IE by IB equal to? Nighat Qadir?
Sir?
What is IE by IB equal to, beta?
Sir, beta.
देखो नहीं खुदा इंसान, मैं तो हाईलाइट भी कर रहा
Gamma.
हूँ। It is gamma. It is gamma, है ना? It is gamma. What is IB by I1? It is 1. And खुशबू बताएगी what is IC by IB? खुशबू.
Sir, beta.
It is beta. So gamma is equal to 1 plus beta. If you remember, मैंने कहीं पे आपको बताया था the value of gamma, कहाँ पे मैंने कहा, हाँ यहाँ पे मैंने कहा था the value of gamma is nearly equal to beta, and I said that in fact gamma is equal to beta plus 1. Gamma is always equal to beta plus 1. Gamma is always equal to beta plus 1. Okay, gamma is equal to beta plus 1. And we also know that what is the relationship of beta and alpha? Beta is equal to alpha divided by 1 minus alpha. Okay, beta is equal to alpha divided by 1 minus alpha. Using this equation in above, ये ऊपर हम use करेंगे. In equation A, for example, in equation A, so we will have gamma is equal to alpha divided by 1 minus alpha plus 1. Okay, plus 1. So we can simplify them. It will be alpha plus 1 minus alpha divided by 1 minus alpha. It is equal to gamma. Then you have a negative term here. Then you have another negative term here. Then you can say that gamma is equal to 1 divided by 1 minus alpha, and it is also equal to beta plus 1. It is equal to beta plus 1. This is the relationship between alpha, beta, and gamma. Now see, you have to, there's a smaller assignment. You have to find how this equation is valid. ये आपको मैंने reverse saturation current शायद मैंने इसकी common emitter की नहीं निकाली, I don't know मैंने निकाली कि नहीं, but you can find it out from common emitter configuration that beta and alpha are related by this relationship. ये आपको निकालना है, ठीक है, ये आप घर में देखेंगे. Is it fine? So this is the relationship between gamma, alpha and beta. So these are all 3 different current gains. ये जो सारे हैं ये क्या है, ये है current gains. तो this is how they are related. कोई सवाल तो नहीं है? अबरार है यहाँ पे, अबरार बेटा कोई सवाल तो नहीं है?
सर सर बीजेटीज को हम करते हैं ना मोस्ट कॉमनली यूज लो करंट एप्लीकेशंस के लिए। तो हाई पावर एप्लीकेशन जहाँ पे होती है वहाँ पे हम क्या यूज करते हैं, ट्रांजिस्टर्स या फिर कुछ और डिवाइस?
देखिए बीजेटीज में भी 2 तरीके की बीजेटी होती हैं. अगर आपको पावर बीजेटीज होंगी तो आप उनको हाई पावर के लिए यूज कर सकते हैं। नॉर्मल बीजेटीज को हम करते हैं लो पावर डिवाइस, लो पावर एप्लीकेशंस के लिए यूज। बट इफ यू वांट टू सी, इफ यू हैव हाई पावर एप्लीकेशंस लाइक एम्पलीफायर्स या स्पीकर्स हैं या कुछ और हैं, काफ़ी ज़्यादा हीट डिसिपेट होती है, अब काफ़ी पावर हैंडलिंग होगी, उसके लिए हमारे पास स्पेशल बीजेटी, उनको कहते हैं पावर बीजेटीज। तो पावर बीजेटीज यूज हो जाती हैं। तो कहीं कहीं अगर पावर बीजेटीज भी नहीं तो कुछ और डिवाइसेस हैं जैसे मॉसफेट्स वगैरह हैं, तो उनको भी आप कर सकते हो पावर मॉसफेट। लेकिन पावर बीजेटीज हैं नॉर्मल बीजेटीज के अलावा एक और ऑप्शन जो हाई पावर एप्लीकेशन के लिए यूज हो जाती है, एंड विल स्टडी दोस बीजेटीज आल्सो। और कोई सवाल है किसी को? और कोई सवाल है? Okay, if there is no question, then I'll summarize my discussion about common emitter, common base, and common collector configuration. Okay, so first I'll try to make um, a diagram here. So this
सर
is
कैन वी स्टॉप बिकॉज हमें लिंक आ गई है कम्युनिकेशन की।
okay. Okay, I'll stop, but I may be taking some extra classes also. तो I'll stop here right now. ठीक है, कोई बात नहीं है, we can stop. लेकिन आप थोड़े एक्स्ट्रा क्लासेस के लिए आपको you have to bear with me. तो I'll take quickly your attendance और जिनकी मैं लूँगा उसके बाद आप निकल सकते हैं आराम से। Just give me 1 minute. जिनके नाम मैं लूँगा वो निकल सकते हैं। 10 is present, 13 is, then we have 14, 15, 17, you can leave जिनके मैं नाम ले रहा हूँ। 18, 26 भी प्रेजेंट है, 27 भी है, 29 भी है, then we have 30, अच्छा 29, okay. So then we have 38. 38 is present. 45 is also present. Then we have 46, 51, 54 भी है, 60 भी है, 60, okay. 65, 6, 70, 7, 2, 3, 4, 5, 77 और 76 एब्सेंट है। अच्छा 78 भी है, तो 76 इज एब्सेंट। ठीक है, आप जा सकते हो।